Good morning, everyone. Thank you very much, first of all, for the introduction, as well as for the opportunity to present to you this morning. As Louis said, I'm from the University of Strathclyde. I'm head of signal processing there. And within the UK community, for the last 15 years, we've worked on a technique which we called polynomial matrix decompositions. So the other two people I've thanked here, Professor John McWhirter and Professor Ian Proudler, are co-enthusiasts in this technique. And what I'm presenting you today is the effort that our groups have basically driven over the last decade. Over the last number of years, we had some good support as well from the UK research councils. We've basically ramped up these efforts, and I'll give you a little bit of a flavor of what we have developed, and hopefully maybe what you might be able to do with this as well. So the title is Narrowband Descriptions and Optimal Solutions, basically extending these to broadband arrays. In my overview, I've actually got quite a lot of material here, more material that I will be presenting. So I will give you a little bit of an overview of what polynomial matrices are, where they arise, and then what type of problems you can actually use to describe them. Is this something that I should not be doing? Yeah, hopefully. Yeah, we've got to deal with a lot of noise. That's our business as signal processing engineers. So that was rather bursty. So I'll introduce you to some of the polynomial matrix operations where these come from, and then a way to solutions are in factorisations of these matrices. So that's the first part, and the second part I will concentrate on two applications. One is for broadband beamforming. The second one is for angle of arrival estimation, just to give you a flavor of where these techniques can be applied. So where does the polynomial matrix come from? What does it look like? So a polynomial matrix is basically a matrix that either has matrix-valued coefficients. So for example, here you have a polynomial in Z, and you have 2 by 2 matrices as the coefficients. Or you could also have a matrix, and each entry to this matrix is a polynomial in itself. So it's not a constant matrix, it has polynomial entries. Now, if you, for example, think about a communication system, if you deal with MIMO communications and you do a channel measurement, then you might have, for example, 2 transmit and 2 receive antennas, and the channels that you span between these pairs of antennas are generally FIR filters. They're not just a narrowband system, they're representing an impulse response. So what you could do is you could take this matrix and basically write these impulse responses